Hydrology and water resources, one of the biggest sessions, always in these meetings, lots of use and applications for our data products in that domain. Meng Zhao is going to kick us off from the University of Idaho, talking about substantial root zone water storage capacity observed by the GRACE missions. As before, Manish will keep the time. After 3.5 minutes, we'll give you a 1-minute warning. So go ahead, Meng, please.
Okay, thanks. I'm going to talk about GRACE applications in ecosystems, especially to understand plant water stress. So plants do not just sip at the surface soil moisture. Roots can actually reach meters deep, track groundwater table, and even pull moisture from the bedrock. So putting a number on this maximum capacity of the ecosystem can store water in the rooting zone is really needed for a lot of ecosystem applications. For example, like to understand plant water stress, to calculate evapotranspiration, to estimate productivity. However, we cannot use field measurements to do this job, and this is exactly where GRACE can help us to estimate at scale, and I will show how. Okay. So here's a very familiar terrestrial water storage time series for southern Idaho. So TWS typically increases during winter because the rain and snow is bigger than the water losses through evapotranspiration and discharge. And then it draws down during the summer season because outgoing evapotranspiration exceeds precipitation. And the magnitude of this annual drawdown is how much terrestrial water storage has been supplied for evapotranspiration each year. It is tempting to call this annual drawdown as root zone water storage capacity, but here are some caveats that we need to account for before we really call this drawdown as root zone water storage capacity. First is the snow storage should not be considered and must be removed. So we exclude those freezing months. And second, the previous year's drawdown may not be fully replenished in winter. A drawdown can happen over multiple years. And in this case, a continuous TWS drawdown occurred from 2011 to 2015. And the difference between the maximum and minimum, we can use that as a proxy for root zone water storage capacity. And one more caveat we need to account for is that we don't want to include groundwater pumping into our root zone water storage capacity estimate because that is artificial human withdrawal. And what we do is we detrend the GRACE time series because the groundwater pumping is typically manifested as a long-term trend in GRACE signal. So with that, what's the global pattern of GRACE SR looks like? So here's the global map of the root zone water storage capacity from GRACE, and the global average is about 220 millimeters. And how does this GRACE-derived estimate compare to other SR products? So there are two other major ways that people estimate SR. One is to multiply rooting depths with the soil holding capacity, and the other is to track the storage drawdown using a simple water balance, which is precipitation minus evapotranspiration. And the maps here show the GRACE-derived SR minus the other two products. Where you see green means GRACE shows a larger root zone water storage capacity than the other two products, and the greens are pretty widespread. And this pattern basically suggests that the other two products underestimate the root zone water storage capacity. And then here's the question, so which estimate is actually closer to reality? And unfortunately, we don't have a real gold standard data set that we can compare it to. So what we do is that we use an independent USGS hydrological model that actually include the SR as its parameter. And we ask a simple question.
1 minute left.
Yeah, sure. So we ask a simple question that's GRACE-based SR makes the model's evapotranspiration simulations better compared to the other two products. And the green areas means, yes, GRACE helps improve the evapotranspiration estimations. And as you can see, there are many of them are green colors, which suggests that GRACE-based SR is probably more closer to reality. So the main takeaways is that the global root zone water storage capacity is much larger than previously thought. Um, in nearly half of the global vegetated areas, the root zone water storage actually exceeds the 2-meter soil capacity, which makes the frequently assumed the 1.5 meters soil depths in a lot of land surface models such as NOMP probably needs to improve their soil depths. We also demonstrate that with the new GRACE-derived SR values actually improves the ET simulations. And this work has just been published in Hydrology and Earth System Science. And that's it. Thanks.
Thank you. Interesting work. We're going to continue with two presentations from your group, but given by different members. First up is Lucas Hoekebouw on leading satellite-based evapotranspiration products insufficiently capture interannual variability evidence from the GRACE missions and in situ observations. Go ahead, Lucas.
Hi, morning. My name is Lucas. I'm a postdoc with Mong Chao at University of Idaho, and here I will show that remote sensing ET products cannot sufficiently capture interannual variability. So interannual variability, or EAV, plays an important role in drought monitoring, land-atmosphere interaction, and water resource planning. Remote sensing-based products are often used to estimate it. However, their module outputs based on inputs like reflectance, soil moisture, and temperature. There's a lot of work validating this data set, but most of that focus on their long-term mean and seasonal cycle, and they're really good. This has been used as supporting evidence for many of these EAV applications, but actually, whether this product capture EAV remains not specifically evaluated. It could sound surprising, but there are not large scale ET measurements for benchmark. So GRACE gives us a nice opportunity to evaluate them at basin scale using the water balance approach. So in this study, we compare the EAV in ET from GRACE water balance against OpenET and GLEAN across the Western US. GRACE-based evapotranspiration is derived from mass conservation. In contrast, OpenET and GLEAN rely on surface process like LAI, net radiation, air temperature, and others. So this example from the Columbian River Basin showed that both OpenET and GLEAN agree well with GRACE at seasonal time series. However, for EAV, there's basically no meaningful relationship. The linear regression slope is less than 1, which means that EAV is underestimated. We also accounted for uncertainties in GRACE water balance by running 1,000 Monte Carlo pseudo simulations. This shows that this reduction in R square is not simply caused by GRACE precipitation or stream flow uncertainty. Well, this sounds pretty shocking. Can we find similar patterns at site scale? And yes, we can. We compare OpenET and GLEAN pixels over 9 Ameriflux basin. We see here that the dark blue column shows that full time series, followed by light yellow column for EAV for all products and both basin and site scale. These patterns basically correspond at both, and this supports our GRACE findings. So in summary, OpenET and GLEAN underestimate GRACE-based EAV by over 6% on average, and this is consistent with Ameriflux results. This likely happens because Pennon-type modules emphasize surface factors like LAI and temperature, while GRACE captures total water storage changes. Our findings have important applications here because they show that using OpenET and GLEAN can overestimate ET sensitivity to vegetation, potentially biasing our understanding of carbon-water interactions. Overall, satellite-based evapotranspiration products need careful validation and evaluation before being used for application relying on accurate interannual variability, like drought monitoring, ecosystem water use, or land atmosphere studies. Okay, thank you so much for your attention, and reach out us in our recent published paper on this topic, and we are happy to answer a question.
Thank you, Lucas. That was really interesting. I wasn't aware of that paper. We'll definitely take a closer look. Okay, next up, we have Yanni Zhao, also University of Idaho, I presume out of your group, talking about global models underestimating hydrological drought, evidence of delay onset, advanced recovery, and reduced severity from the GRACE missions.
Hi everyone. I'm Yanni, a PhD student from University of Idaho working with MON Research Group. Today I'm going to talk about how well global water models capture hydrological drought evolution against GRACE Drought Severity Index. Hydrological models are widely used to forecast drought and to assess potential impacts on human health and socio-economic systems. Early warning and mitigation planning depend on characterizing drought evolution, including onset, peak, duration, and recovery. Although these models are often validated against drought indices, their skill in reproducing this full evolution has not been systematically evaluated. In this study, we use GRACE observations as a benchmark to evaluate the ability of 8 easy-made models to capture the full evolution of drought events. Here I present time series in one MOSCON from both GRACE and model. 3 drought recovery events were identified using the standardized TWSD score, referred to as GRACE Drought Severity Index, or GRACE DSI. From this time series, we determine drought onset date and recovery start date, as I shown in the figure. The drought and recovery durations describe how long each phase lasted, while the minimum DSI value represents drought severity. These indices were then extracted for the corresponding drought events across all 8 easy-made models for comparison with GRACE. Now, to quantify the differences between models and GRACE, we calculate the global mean differences of each drought index, defined as model minus GRACE. We find that the drought onset differences are all positive in the first column, indicating that models simulate a later onset compared to GRACE. In contrast, 6 models show negative recovery start date differences, suggesting that they recover earlier than GRACE. For duration, nearly all models simulate shorter drought and recovery periods. Finally, for the peak DSI, models generally show higher TWS values during droughts, indicating that they underestimate drought severity. So what factors may cause the model biases relative to GRACE? We explored the roles of precipitation, temperature, area, and aridity classification across different stages of drought evolution, using CWTM model as an example. For drought onset, we found that when precipitation is above the median, models tend to delay drought onset date. Similarly, when precipitation is higher, models simulate shorter drought durations. For recovery, models generally recover faster than GRACE, especially in those drier regions. These patterns are consistent across all 8 easy-made models. Here are some takeaways. So our results show models systematically underestimate hydrological drought, which is consistent with findings from recent study. In addition, we found model droughts start later, recover faster, and are shorter in duration, and less severe compared to GRACE observations. Finally, the climate conditions help explain part of these model biases. So that's it. Thank you.
Thank you, Yanni. Appreciate your presentation. We'll keep going. Next up, we have our own JT Rieger from JPL. JT is going to talk about drought from top to bottom, advancing understanding of processes with GRACE missions. JT, we don't hear you yet. I don't know if you're muted.
Okay,
Yeah.
Sorry. Okay.
Okay.
Okay, so the title of this talk is Drought from Top to Bottom. It's a little bit of a review paper talk, but it's also talking about drought through the soil column. So it's a clever title. Let's see here. Why observe drought from space? Well, mostly because droughts are hard to see in the subsurface, and that's where a lot of drought activity happens. And so gravity observations that can capture events and event transitions actually give us new information on drought in the soil column and what it looks like. The basic scientific challenge is we just don't know soil residence time of water and soil drainage very well globally. And that's because we don't have great information on the subsurface. So we've been able to use gravity observations from GRACE and GRACE follow-on to really teach us something about how droughts work and evolve. Really, just to flash back a little bit, the foundational advance in this work came in 2014 in a paper by Elise Thomas and others on this water storage deficit framework. And that's when we take an actual water storage monthly variation. We do something simple like calculate a normal range of climatology and then measure a standardized difference from that climatology. And so everything you see like GRACE-based drought severity indices, those types of things, they're based on this one. So with this allowed us to, for the first time, actually assess how much water is missing during a drought and for how long. And it also, by normalizing, allows us to compare droughts at various locations. So what's a drought for one region might be different in magnitude than what constitutes a drought in another region. So that was that work. Building on that, so we can see, when a drought begins, when a drought ends, the size of the total water storage deficit, and then these peak missing amounts of water during a drought event. Then building on that work, two other papers came out, one in 2019 and 2021. The first question we asked 2019 was, well, if we can figure out how much water is missing, then we could estimate how long it takes to get back to normal. And if we know something about precipitation and precipitation statistics for a region, we can even estimate the likely time required to get back to normal. So that's that work. And in Farhamand et al. 2021 was a postdoc, both of these were postdocs here at JPL, Alka and Ali Reza. Then we worked on this concept of drought cascades, which is actually incorporating other data sets like precipitation, VPD, surface soil moisture from SMAP, and terrestrial water storage to see this kind of propagation of the drought signal from the atmosphere down through the surface soil column and into the deeper soil column with time. So that really uncovers something that we referred to as cascade dynamics and introduced this concept of drought cascades. Then kind of the peak of all of this, and this is my last slide, is work by Daniel Blank et al. From 2025. Daniel's a postdoc with Annette Eicher, and using observations of soil moisture from SMAP and SMOS and an ESA CCI data set, along with daily ITGS GRACE follow-on solutions, we were able to combine all of these techniques to really show how drought propagates through the surface to the root zone and then into deeper layers that include total water storage, and how therefore recovery time in each of those layers takes longer. And this is really how drought signals dampen and delay as they propagate downward, and why groundwater and deeper storage losses really do take years to recover. So this paper is in Water Resources Research. If you're interested in reading more details about it, it's available, and the slides are online. So I will just say that GRACE missions have really transformed drought science from static deficits to dynamic layered processes. We now have the opportunity to do multi-sensor integration with soil layers and depth for understanding drought cascades and layered recovery. I think the remaining frontiers are to actually see what plant responses are as that water starts to shift down through the soil column, and we can find those drought-resilient plants and rooting depths, and that all of these methods could be combined into a next-generation global drought observatory. Okay, thank you.
Thank you, JT, for that overview. Really appreciate that. We'll keep going. Again, use the chat for questions now, and we'll follow up later, also after the session for a Q&A session. So next up, we have Carter Smith, CU Boulder. Grace, following observations of small-scale hydrological signals, preliminary results for the Lake Mead surface water. Carter, you ready to go?
Sorry, I was muted. Yes, the preliminary results for Lake Mead surface water. I'm Carter Smith. I'm a junior aerospace engineering student at CU Boulder. I've been working under the guidance of Dr. Khosrow Gobadi-Farr. The motivations of my study: we know GRACE and GRACE-following satellites are perfect for measuring terrestrial water storage at spatial scales larger than 300 kilometers. Our study aims at pushing the limit of GRACE for monitoring much smaller scale hydrological signals with a case study on Lake Mead water storage. And the findings from this study will be applied to study other small-scale mass changes, like the snowpack over Sierra Nevada. We used the MASCON data from the JPL, Goddard, and CSR. These are the tiles that we studied, the Goddard and CSR tile and the JPL tile with 3 degree by 3 degree spatial resolution. And here's the mass changes that we detected across 3 solutions. There's a lot of alignment between the 3 of them. So we decided that we could track just the Lake Mead storage if we could remove all that other hydrological signals from the total water storage. And these included soil moisture, surface water, except for Lake Mead, like rivers and wetlands and groundwater storage. These were the signals that we picked up from the GLDAS, NOAA, and WGHM models. The largest signals came from soil moisture, and there were smaller signals coming from rivers, wetlands, and groundwater. And then after we removed these signals from the original GRACE data, we actually saw significant alignment between the new corrected data and the Lake Mead NC2 volume data, which was really incredible that such a small area, which is Lake Mead, could be detected when it's used to spatial resolutions of 3 degrees by 3 degrees. There is still some disagreement. We believe this is because we couldn't accurately detect all the outside hydrological signals, and we are working on finding models that could correctly detect these discrepancies so we can close the gap between the GRACE data and the volume data, but still incredible that we get this level of seasonal and interannual variability in the accuracy. Here's a comparison of the JPL, Goddard, and CSR MASCON data that we found. JPL, Goddard, and CSR here. We saw the most agreement between the JPL data on that small scale resolution. And finally, I just wanted to perform a water budget analysis using the GRACE and GLDAS NOAA to prove that outside models could correctly model our GRACE data to see if we could correctly find models, then we could remove that outside water and get these corrections for like a Lake Mead storage, a much smaller scale. So these are the P and ET data we got from GLDAS, and the USGS gauge data we got the discharge, and the rate of change of the total water storage we got from GRACE. And it was very, very accurately modeled when we performed the water budget analysis. And it was incredible that these outside models could correctly model our GRACE data, and also examples of seasonal variability and interannual variability. So now we need to apply these models and take out other hydrological signals so that we can eventually track very small scale hydrological changes like Lake Mead or Sierra Nevada snowpack with GRACE. Thank you, and let me know if you have any questions.
Thank you, Carter. All right, we'll save questions for the discussion session. We'll move on. Next up, we have Kevin Gostra, who's a postdoc here at JPL, on the effect of lake water storage change in Canada on GRACE, GRACE follow-on, and GNSS station displacements, implication for subsurface water.
Thanks, Felix. Can you guys hear me and see the slides?
Yes, we can.
Okay. Yeah, so as Felix mentioned, I'm a postdoc at JPL, and I'm here to present kind of an update on a lake water storage data set we've been producing to try to estimate its impacts on both GRACE and GNSS. There we go. So last year we presented some work looking at a global scale lake water storage data set where we took time series of changes in lake water storage from October of 1992 to October of 2020 for around 1,000 lakes globally, made maps of that lake water storage change, and then predicted how it would affect GRACE and GNSS differently. But there were some weaknesses in this global analysis that we did, mainly in high latitude regions where temporal sampling of lakes was quite poor. And that's shown on this slide. You can see in the upper left, all of the blue lakes are lakes that we were aware of and managed to include. They passed our quality criteria for high enough temporal sampling of their volume storage change. And orange lakes are lakes that we were aware of but had to exclude because they failed this quality criteria. Those quality criteria are on the upper right there. And to try to fix this, we went and gathered 3,066 gauges from the Water Survey of Canada, as well as new altimetric data from GREALM dominantly, and combined those together into a kind of composite lake water elevation time series to estimate new changes in lake water volume from October of 1992 to May of 2025, extending the time series and increasing the number of lakes that we could accurately or adequately model the time series of to 405 over the region of Canada and upper contiguous North America. The kind of long-term punchline of what this looks like from GRACE's perspective is shown here. The top row is the trend from April of 2002 to April of 2025 for lake water storage on the far left, snow water equivalent from aerified land on the center left, and GRACE terrestrial water storage from the JPL MASCON solution on the center right. And then the far right is what we're calling subsurface water, which we're taking to be terrestrial water storage from GRACE minus the lake water, minus the snow water. The center row is the half amplitude of the seasonal, and then the bottom row is the month at which we have maximum water for each of those water storage components. The large-scale observations we made at this point in the analysis were that terrestrial water storage seems to peak typically after snow melts, but before lake water fully recharges and before subsurface water recharges. The other main observation was that there's a much larger decline, if you look in the upper right, trend map in Western Canada for subsurface water than in Eastern Canada over Eastern Ontario and Quebec. We also did a basin scale analysis. This is for 4 basins, which are some of the largest basins in Canada and into the contiguous US. The Great Lakes, the Nelson River, the Keweenaw-Churchill River Basin, and finally the Mackenzie River Basin. On the left, I'm showing the surface water in the dark blue time series, the snow water from aerified land in the light blue, and then the orange is showing GRACE terrestrial water storage change. And some high-level analysis that we saw here was just that all 4 of these basins have experienced a substantial decline in TWS in the GRACE time series over the last 3 or 4 years, with the Great Lakes peaking in around 2021 and then declining over the last 3 or 4 years. But most of that decline in the Great Lakes Basin can be attributed to surface water change. However, we can rule out surface water change, either snow or lake water, being the driver in the Nelson, Keweenaw, and Churchill.
1 minute left.
Okay, thanks, Manish. And so we interpret the loss of TWS in these other 3 basins as being some kind of decline in subsurface water over this interval. So just to summarize, we added a bunch of gauge data to new altimetry data to update the lakes in Canada. We've found that the timing of Grace TWS is kind of interestingly between snow and lake water recharge in this cold weather region. There's a greater decline in subsurface water in Western than Eastern Canada. We're still testing to see if there's any GIA explanation to that long-term trend. And over the last 3 years, there's been a precipitous decline, which is not explained by lake or snow water in some of the larger basins in Western Canada. Thank you.
Thank you, Kevin. All right, we'll move right along here. Next up, we have Avery Sanchez, also from CU Boulder, looking into 2024 European precipitation anomalies with GLDAS and GRACE follow-on data.
Yes, hello, my name is Avery Sanchez. I am an undergraduate at the University of Michigan, but I had the opportunity to conduct research this summer at CU Boulder under Dr. Khosrow Gobadi-Farr. And today I'm going to be talking about the comparison of observed 2024 European east-west precipitation, contrast with the GRACE terrestrial water storage mass consolutions. So first, we're going to look through some previous years' annual average precipitation from the GLDAS. So you can see in each of these years, we notice some potentially unique precipitation anomalies. We can see the pattern shifting year to year, and it kind of shifts during the duration of this model. But what is most interesting is the pattern that we observe in 2024. So we can see that there is this unique, distinct contrast between Western Europe and Eastern Europe, where Western Europe has significantly higher precipitation flux over the year, and Eastern Europe has significantly lower precipitation flux. And we can see in the previous years that this is a unique contrast. And so we were wanting to investigate and see if this contrast translates at all to the GRACE TWS mass consolutions. So we know that this is a precipitation flux, and it won't directly contribute directly to the TWS solutions, but we were curious to see if it still translates and how we can observe that. So looking at the GRACE solutions, we can see that in 2024, we do see this contrast where the Western has less negative TWS and the Eastern has more negative TWS. And looking in previous years that align with the previous precipitation years that were in the previous slide, we can see that this is a unique contrast, which was exciting to see. And so then looking into the temporal evolution of TWS, this is with the climatology removed. If we highlight the 2024, we can see that there is this sharp drop-off in Eastern Europe, which is unique. But more notable is that we can see that Western Europe continues to have, it remains consistent through spring and summer, which is where we would expect to see decreasing of the liquid water equivalent. So that's particularly interesting, and it aligns with what we see in the spatial plots as well. And so continuing further, we're interested in identifying potentially which storage component contributes most to this TWS that we observe. So looking at the total soil moisture, we do see that there is a similar contrast that was observed in the precipitation plots. So we can see that there is a higher soil equivalent water height in soil moisture in Western Europe as compared to Eastern Europe. And this is not observed in the snow water equivalent. So we can kind of deduce that the total soil moisture likely contributed most to this the grading we see in the GRACE TWS solutions. So just some takeaways. We see this exceptional east-west contrast over Europe in precipitation in 2024. Through observing previous years, we don't see this same contrast. And we do see that this contrast can be observed in the GRACE TWS solutions as well. So we see that it does translate And we see that pattern with the eastern and western contrast again. And we can deduce that this distinct TWS pattern was mainly driven by soil moisture. Thank you. If you have any questions, please direct them to my email.
Thank you, Avery. Appreciate your presentation. We'll move right along. We're about halfway, or just about halfway through to this hydrology session, so we've got a few more talks. Next up is a presentation on using GRACE satellite data to analyze spatial temporal variations in groundwater storage in the Bug Basin near the Polish-Ukrainian Belarusian borderland, given by Justyna Sliwinska. You can see your slide. I don't hear your audio right now.
Okay, hello. Good
Oh, now I
morning.
do, yes.
So great. So, yes, our work concerns the analysis of temporal and spatial variability in terrestrial water storage, and especially in groundwater storage in a relatively small area of approximately 40,000 kilometers squared, namely Bug River Basin, at the border of Poland, Ukraine, and Belarus. The key aspect is introducing an improved method of estimating satellite-based groundwater storage using GRACE and hydrological model with three key innovations. The first one is downscaling GRACE data to 0.1 degree grids using random forests and high-resolution precipitation, evapotranspiration, runoff, and soil moisture as predictors. But the most important is a modified method for groundwater storage calculation, which takes into account depth to groundwater table and associated delay in response of groundwater to changes for example, by precipitation and evapotranspiration. So this is the most important aspect of our work. But we also made some calibration of satellite-based groundwater storage to better represent observed variations in groundwater at in situ monitoring points. And to do so, we use random forests for setting temporal and kriging for spatial relationships between satellite and in situ data. So here we can see some basic results. In general, our approach allowed us to obtain correlations between GRACE-derived and in situ groundwater storage ranging from 0.66 to 0.95 at monitoring points, as seen in the right-hand side plot. But if we take into account the depth to the groundwater table, we do see that the lowest correlations are for the areas with the deepest groundwater table. And looking into trends and annual signals in terrestrial water storage and groundwater storage averaged over the study area, we can see that trend in terrestrial water storage is decreasing around 9 millimeters per year. But at the same time, trend in groundwater storage is close to zero, which may indicate somehow some kind of resistance of groundwater resources in this river basin to meteorological factors from, for example, precipitation and evapotranspiration. At the same time, we do see that seasonal signal is strong for both terrestrial and groundwater storage, but terrestrial water storage exhibits about 4 times higher amplitudes of the annual signal. We also do see some shift between terrestrial and groundwater storage of around 1 month. And to conclude, two main take-home messages are that taking into account groundwater level depth while calculating satellite-based groundwater storage variations can increase the consistency between satellite-derived and in-situ groundwater storage, especially for shallow aquifers. And this is important aspect in monitoring of transboundary river basins, where we can sometimes have no data from neighboring countries. And we also see that the zero trend in groundwater storage combined with negative trends in terrestrial water storage may indicate that water losses mainly concern the unsaturated zone, and resources in this particular river basin are resistant to changes associated with some climate impacts, for example. So that's it. Thank you for your attention.
Thank you, Justina. Moving right along. Next up, we have Karim Abdelmozen from Arizona State, talking about assessment of groundwater variability in the MENA region, identifying key controlling factors.
Hello, everyone. I'm Karim Abdelmozen. I'm a research scientist in Arizona State University. And can you see my screen?
Yes, we can.
Okay, perfect. And my topic today is assessment of the groundwater variability in the MENA region, identify key controlling factors. And by looking to the general trend from GRACE, we can see some areas in the Middle East that witness a recharge signal from GRACE, as we can see here. And because of time, we are going to discuss only two case studies from the Mediterranean coast and the Nile Basin. And here is the cyclone Danielle that affect actually the coast area of Libya. And from the planet land images here, we can see how the land surface impact of this extreme event before and after this cyclone. And as we can see from precipitation data, it was a unique precipitation event in this period. And by investigating the GRACE time series over the area that affected by the cyclone, we observed a signal of water mass increase that might indicate a recharge of the North Kofra basin, as we can see here in area 1 and 2 and 3 and 4 and 6 of GRACE time series. Another case study from the Nile Basin, and the Nile Basin has a sub-basins, actually White Nile sub-basin and the Blue Nile sub-basin and the Abara sub-basin. And since 22, actually, the Nile Basin, particularly Sudan, are witnessing flood events and extreme precipitation events over different sub-basins. And here we can see how the effect of this flood events actually is that increased the width of the White Nile River and the Blue Nile River. And we can see here in 2016 and here in 2020 how the increase of the White Nile River increased and the Blue Nile River increased as well. And here is a recent image from Sentinel-2, and it's showing actually an increase even in 25 from months of August actually until September, and we can see it almost double of the width of the White Nile River, and the same for the Blue River. And this area actually start witnessing an increase of water flow from 350 million cubic meters to 750 million cubic meters, almost double of the flow, and the increase in the water level in the Nile River by 2 meters. So what actually the source of this increase that we observed in the White Nile River and the Blue Nile River, and by taking the difference images from the GRACE, we can see a concentration and increase in the mass over the Blue Nile sub-basin and the White Nile sub-basin that indicated by the blue areas. and the same over the area of Lake Nasser in Egypt. And by looking to the precipitation and areas that witnessing increase from the first period to the second period, actually, we found the Blue Nile Basin area, and the White Nile Basin has an increase of more than 100 millimeters of precipitation. So as a second step, actually, we're trying to see what might be the main factors or drivers of this increase in these areas in the Middle East or MENA region by estimating the human groundwater depletion. And to do that, actually, we need to estimate the soil moisture in these areas and the natural recharge, identify the natural recharge in these areas from precipitation, and managed recharge in these areas. And by identifying this and integrating
1 minute
variables.
left.
Okay, thank you. And identifying these variables and integrating with GRACE, we should be able to identify the human groundwater depletion part in these areas. Thank you.
Thank you. Then we'll continue in the regular program here with a talk on validating OS list flood with SLR, 3 decades of hydrological variability. That's going to be given by Philip Yaldin. Philip, are you ready to go?
Yes.
Sorry if I put you on the spot here with short notice, but looks like you're ready. Take it away.
Yes. So good morning, evening, everyone. My name is Philip Gaudon from Wrocław University of Environmental and Life Sciences. I briefly present our study about validating the OS list flood with SLR data, the 3 decades. All main goals are threefold. First, to evaluate the performance of the OS list flood hydrological model and compare it with LSDM model. Of course, in producing a terrestrial water storage variability across the largest river basins. Second, to analyze the spatial and climatic patterns and identify where each model performed best. And finally, to validate these models using independent gravimetric data sets. So combination of SLR plus GRACE, SLR plus GRACE plus DORIS, extending the record back to the pre-GRACE era. We use 3 reference data set, so SLR only solution up to degree and order 10, and 2 combined models, SLR plus GRACE, which was presented in last GRACE follow-on science team meeting, and SLR plus DORIS, which is SLR plus GRACE plus DORIS, both up to degree and order 60. The key findings from this plot, which is shown based on the spectral analysis in 100 river basins, the signal characteristics remains consistent, and between the pre-GRACE and entire period, it confirmed that the stability and reliability on combined data set. Therefore, in the presentation, we focus only on the combined models and comparison with combined models. Here we compare both model against SLR plus GRACE and SLR plus DORIS over the nearly 30 years. And OS list flood clearly outperforms LSDM model, of course, in particular in tropical and subtropical regions for the trended signals, while LSDM remains competitive in Asia and high latitudes for interannual signal. The spatial consistency between both gravimetric combination confirms the robustness and of our results. The scatter plot show quantitative agreement using the centered modified Klein-Gupta efficiency, where OS list flood reached a median CKJE of 0.59 for the trended and 0.41 for interannual signal. It is almost twice that of LSDM median. The model is most consistent with gravimetric estimate in large low latitude basins, such as Amazon, Congo, and Niger, which demonstrate that the OS list flood captures more realistic seasonal and interannual amplitudes. When we're focusing on the pre-GRACE decade, we see similar consistency between SLR plus Grace and SLR plus Doris. Here also OS Listwood outperforms LSDM, particularly in tropical and subtropical regions, achieving positive NSA values, while both models still struggle in high latitude and arid basins. So to summarize, OS Listwood outperforms LSDM. It better captures large-scale TWS variability, especially seasonal and interannual signals. In tropical and subtropical regions, we have strong agreement in pre-Grace era with SLR plus Grace and SLR plus Doris. And it confirmed that the OS Listwood reproduce more realistic interannual TWS before 2002. And at high altitudes and in arid regions, both models still struggle to reproduce realistic TWS variabilities, often underestimate interannual amplitudes. It's all from my side. Thank you for your attention.
Thank you, Philip. All right, we'll move right along here in our program. So next up, unfortunately, Matt Rodell cannot join us, but his colleague Mary O'Neill is able to give his presentation on assessing the seasonal cycle of terrestrial water storage with L1B stacking. All right, yep.
All right, did that work? Does that work well?
Yeah, we see it now, full presentation mode, and we can see and hear you. Go ahead.
Okay, great. My name is Mary Michael O'Neill. I'm a postdoc at the University of Maryland and at NASA. And my co-authors, Matt and Bryant, can't be here today. So I'll show some of Matt's slides and then show my own on a similar method. In both these talks, I'm going to be talking about a method that Bryant and Matt and I have been working on that leverages this trade-off between spatial and temporal resolution. As hydrologists, we typically use the level 3 GRACE products that are provided at monthly time steps. We have recoverable signals with those around 150,000 square kilometers. But there's been increasing amount of work that's kind of pushed the limit of this trade-off between spatial and temporal resolution, where you can get down to daily signals if we're okay with a smoother picture or higher spatial uncertainty. And then recent work by several groups, including Bryant, have shown that if we're willing to sacrifice the temporal component, we can look at much higher spatial resolutions, recoverable signals down to a little over 12,000 square kilometers. The figure on the right is from Bryant's paper in JGR Solid Earth that's looking at ice sheet modeling, ice sheet signals, and essentially found that this level 1B stacking approach, which is what I'm talking about today, can better capture long-term storage trends over ice sheets. And how this works is essentially, instead of performing a regression or an analysis on the monthly data, we directly regress the level 1B data. And so we're not getting, monthly maps of terrestrial water storage anomalies. Instead, we have a single field. In the case of the study on the right, it's trend, and in these slides I'll be showing a seasonal amplitude, so we get a mean seasonal amplitude globally. And so what this might look like, this is an example over the Amazon River. These are seasonal amplitudes. The maps are peak to peak from monthly means. And so in this case, we have found a monthly mean anomaly for each January, each February, each March March. And then the spatial plots are the amplitude. So the high seasonal high minus the seasonal low. And the black line in the time series shown in the center is just isolating a single mascon. What this might look like if we use the black line is just the monthly mascon. So this is the typical product that most hydrologists use. And then the blue line is what would happen if we instead directly regress the level 1B data. The results are just slightly different. The maps it's hard to see the visual differences. But at a large scale, we actually see some reduced spatial autocorrelation. So less leakage, less smoothing. And then if you look at that difference plot, you see that right along the Amazon River, we're seeing a much higher seasonal amplitude. And we could even get a little bit of a stronger signal capture. We could see a stronger signal capture if we fit a single regression term like a sinusoid. And if we aggregate to a spatial resolution of about a major basin size, the differences are slight, but they consistently favor the level 1B regression with higher amplitudes. And those differences are more important for smaller basins. And these are kind of tentative results, but some of the biggest differences that we see are over major lakes. We really see the seasonal amplitude kind of light up when we do this level 1B regression. Then I guess I'll just go straight on into my slides because this is using that same method, that level 1B stacking approach, but instead of looking at seasonal signals, we're looking at trends in terrestrial water storage anomaly over the Sahara Desert. And so again, we're looking at this higher spatial resolution, terrestrial water storage trends using this level 1B stacking approach. We chose to do this analysis over somewhat normal climate conditions. GRACE follow-on years after 2020 were excluded because of this massive cyclone that occurred in March of 2020. It was the wettest month in something like 40 years. And we're also looking at specifically regions that are heavily irrigated in the very deep remote desert. I've highlighted some of these regions. We've got the Northwestern Sahara Aquifer System, 2 pumping fields for the Great Man-Made River in Libya, and then several oases in Egypt. And then also looking at Lake Nasser and the overflow Toshka lakes. And the maps on the left show the differences between, on the top would be the terrestrial water storage trend if we are just using regression across the Goddard monthly mascons. And then on the lower is if we use that level 1B regression. And what we see here are these hot spots where there's intense agriculture really light up. The biggest differences are in the Great Man-Made River phases 1 and 2 in Libya, and region 4, which is East Oanat. It's this very small agricultural outpost in Egypt. In the inset there, you can see a zoomed in visual of it, and it's less than 12,000 square kilometers, and the area makes up well under 1%, actually I think less than 0.1% of land area for the Nubian Sandstone Aquifer, but the total amount of storage loss that we see actually accounts for something like 10% of the trend. We also saw that when we use the level 1B regression in region 8, we actually see the sign flip. So instead of seeing a decrease in those mascons, we're actually seeing increase right over the Nasser and Toshka lakes, which is supported by lake altimetry on the bottom right. And then overall, the major improvements that we're seeing from level 1B regression on the left gives you an idea of the signal to noise ratio. These are the RMS of terrestrial water storage trends for different regions. We've got the highest trend regions or the largest magnitude versus the lower magnitude regions like the remote Sahara or the quiet ocean. And what we see is this level 1B stacking, this regression approach, L1BS, shows the highest RMS over the highest signal areas, but then without sacrificing noise. So we're still seeing low RMS over the quiet ocean. We also see considerably reduced autocorrelation. Some of this autocorrelation is, of course, just from climate and hydroclimate factors that are heavily autocorrelated, but then some of it would also be from leakage and uncertainty. So seeing a reduction in that is helpful. And one of the most interesting results that we found is this relationship between terrestrial water storage trend and groundwater irrigated cropland extent. These are area aggregated trends and cropland extent for those 8 regions I mentioned, and then also other irrigated land in the Sahara. And we're essentially seeing much more negative trends, larger groundwater or terrestrial water storage depletion with higher groundwater irrigated cropland extent. But that relationship is only captured using this level 1B regression and not using just the regression of regular monthly mascons. So I think this is pretty promising, and feel free to reach out to me with questions, or after the shutdown, you can reach out to Matt or Bryant. Thank you.
Thank you, Mary. That was very cool stuff. We'll move right along here. We're on the final lap for this session. 3 more talks. Next up, we have Susanna Wert from Virginia Tech talking about time series of groundwater storage change via GRACE, GNSS, and NCAR integration.
Hello, everyone. Can you hear me?
Yes, we can hear you, we can see you, and your slides are coming up.
Okay.
Now they're up. You're ready to go.
Okay. Thank you so much. I want to talk, I'll give an update about a project on producing a high resolution time series of groundwater as well as total water storage change via an integration of GRACE observations with GNSS and NCAR observations. On the bottom right, you see the sketch of our study area, which is the Central Valley in California. We chose this area because it has plenty suite of observations, including the geodetic observations I just mentioned, but also hydrological and geological data. At the same time, the area is experiencing heavy agricultural use and strong groundwater pumping, which also cause an intense deformation signal. There's 2 types of deformation processes that are occurring. One is the crustal elastic loading, which leads to uplift of the crust due to or decrease of water, and subsidence due to increase of water. At the same time, our aquifers, we observe a poroelastic aquifer deformation, which is especially happening in confined aquifers where decline in water pressure leads to a vertical land motion. Both of these processes actually overlap, especially over aquifers here depicted during a drought event. You see elastic loading leads to uplift of the surface, but over the aquifer here in the middle, we have an overprint of this loading effect due to poroelastic aquifer compaction. In the case of wet here, this would be the opposite. The deformation effect would be the opposite. So what kind of observations are we using? I already mentioned generally, but in detail, we're using the GRACE JPL mascons over the last years. We also have collected processed GNSS data over the region from the Nevada Geodetic Laboratory. For a monthly time series, we get about 500 sites that are eligible, and after some quality assessments. And then lastly, we are doing an in-house processing at Virginia Tech of SAR Sentinel-1 acquisitions. We have worked or processed about 4,000 images on 5 paths and 25 frames using the Babinzar software and providing us with a continuous signal in space and time since 2016. So now we're using all these observations in an inversion model. This is depicted here at the top. On the left side, you see the observations that I just mentioned, including some residuals. And then on the right side, we see poroelastic and elastic Green's functions in this G matrix, which is fed basically by model formulations on the poroelastic aquifer compaction and elastic loading processes. And then at last, we see the parameter X, which include two components, which is groundwater storage change as well as not groundwater storage change, and both of them adding up to total water storage change. And we are inverting this model in a least square scheme, including all these observations. On the next slide, I want to show some results. First, on the left side, these results were already published last year, where we first applied this inversion framework for a single rate during a drought. Just for comparison, we see here on the top left the total water storage change estimated by this inversion scheme, a very typical pattern during drought in California. We have a lot of loss over the aquifer, but also in the mountain areas in Northern California. And then on the bottom left, you see the groundwater storage change estimate from this inversion scheme. Of course, we have groundwater storage only over the Central Valley, most of that in the south where most of the pumping is happening. If we sum this up over the Central Valley alone, we get a loss of a total water storage change of 21 cubic kilometer and 12 cubic kilometer in groundwater storage change per year during this drought. And now in the time series inversion, I want to show one example that especially
1 minute left.
Drought effect, which is the wet year of 2023. This was the most wet post-drought year since we have GRACE observations in the region. And we now invert this wet year. We get a total water storage change of about 26 cubic kilometer mass gain. Just to note, the color bar is here inverted. So dark colors mean now mass gain. On the top right, again, total water storage, we see a more complex pattern during the post-drought year, especially a lot of gain in the northern area of the Central Valley, but also over the mountains. And then on the bottom right, you see the groundwater storage change in total 5 cubic kilometer for this year. And very interesting, we get also a complex pattern, but very interesting, we have a lot of recharge on the mountain fronts, which is supporting some of the recent study on groundwater recharge in the Central Valley. To summarize this, we could see that groundwater recovery during post-drought is a little bit slower than during the drought, which is a very interesting outcome. In general, on the framework, we showed that this unified physical model that integrates all these different observations, accommodates the different sensitivities of the sensors, and allows us to estimate the time series of groundwater and total water storage. We are still working on some final tuning on some of the inversion parameter and input data sets, as well as on the validation. But once we have the final data set, the next goal is to assimilate this time series into a groundwater model and study groundwater recharge processes in the area. Thank you so much for your attention.
Thank you, Susanna. All right, home stretch here. 2 more talks to go in this session. Next up, we have Arfan Arshad from NCAR talking about GRACE and AI and machine learning enabled scalable mapping and assessment tool for decision relevant water resources management. Arfan, are you able to present? Check if you're here. Don't see Arfan in the participants. Colin, do you see him?
I do not.
Okay. In that case, we'll just move on. Arfan, if you're jumping in later, just ping us here in the chat. Mohammed, are you ready to go with your presentation? Aquifer recharge in arid lands from GRACE and modeling, present and future?
Yes.
Excellent.
Let's do that.
Can you see my screen and can you hear me?
Can hear you. Your screen is up now. And if you go in presentation mode, then you're ready to go.
Okay. Hi everyone. Today we, my students Hassan Saleh and Hadi Karimi and myself, are gonna address aquifer recharge in arid lands, present and future, using GRACE solutions and modeling. Are you seeing my presentation?
Yeah, it's not in presentation mode though.
Okay, hold on. Okay. All
Now
right.
it is. Yes.
Okay, good. So we're talking about extreme events because when it comes to recharge, this is the kind of events that actually cause recharge to happen. You're looking in this diagram on cyclones in Southern Arabian Peninsula. These are the tracks. As you can see in this area and in many parts of the whole world, we're seeing an increase in the number of cyclones and in their intensities. What I want to show you in this diagram is that when these cyclones happens in red columns here, in the red lines here, they constitute a huge portion of the total annual precipitation. The one in 2018 called Macono constituted some 70% of the annual precipitation. The one before it in 2011, 60% of the precipitation, and so on. So when they happen, it's a really big portion of the annual precipitation. So precipitation happens. How do we see that in GRACE? We see that as a jump in GRACE trends, or in actually in the detrended time series. So you're looking at terrestrial water storage and ensemble of CSR, JPL, and Goddard here. For the Macono, which is the largest of them, basically we have an increase of 3.2 kilometers cube, or a recharge of that amount. We call this recharge because we take the 12-month before and the 12-month after, the average for them, and whatever is there basically represents, in our opinion, the recharge from it, basically, because whatever was in the soil has already evaporated in terms of soil moisture and whatnot. Okay, so we did this with also with the in watersheds, in this watershed that actually received this cyclone that we talked about. You're looking at the cyclone of 2018 here. And what we do basically, we use the amount of recharge as a calibration procedure for a runoff model or a hydrodynamic model that we basically construct. And we use this for calibration. And in addition to this, to calibrate the runoff, we actually use the distance traveled along the valleys for a number of these cyclones and match both the observed with the calculated distances. And then hence we have a calibrated runoff and a calibrated recharge, basically. So as you can see, the two blues that you see here, one is, for example, is the modeled, and one is the modeled, and one of them is the observed. And this is a hydrodynamic model results, basically. So we use the GRACE data for calibration purposes in addition to other things. We can use that also, extreme events in the central part of Saudi Arabia, where you actually look at the extreme events here, and again, use these extreme events, try to get the recharge from GRACE data for these events that you see here. Again, the 12-month before, the 12-month after will give you the amount of recharge. And again, to calibrate the runoff, we're not using the distance traveled this time, we're using the depth of the water.
1 minute left.
Okay. So once you have this calibrated model, you could actually use it to predict in the future what will happen in this area. So if you can get precipitation from climatic models in the 21st century and find out that basically there's more precipitation over this particular wadi, you can get the precipitation as input into calibrated model and hence have an idea about what is going to happen to runoff and to recharge that you get it from the calibrated model. Now, basically, we are looking at many aquifers worldwide, and for each aquifer, we identify what we call an extreme event, which is the 95 threshold above or the 99% threshold of precipitation over that particular aquifer. And once we do that, we can look basically at the response of terrestrial water storage. You're looking here at one of these aquifers in Saudi Arabia, one of the aquifers in West Australia. You have 5 kilometers cube worth of water basically added there. The total consumption in Saudi Arabia per year is a 10 kilometer cube So you see the importance of doing these kinds of things. The extreme events can cause something about 75 kilometers cubed in Western Australia here in this aquifer that you see here. For more information about this approach, we just published a couple of papers that you can find more about our techniques in them. Thank you.
Thank you. Appreciate it. Okay, that wraps up this morning's session. I still don't see Arfan in the meeting, so we'll just skip that for today and invite that group to upload their presentation, or maybe check in with them, have that talk tomorrow. Okay, so that concludes our morning talks. We can now move to questions. I invite you again to turn on your video if you're able and willing to do so. It's always nice to have faces in the meeting. I still see slides up. Maybe we can take those down and then move to questions. There was one question in the chat from Chao Yang to Mary. We'll kick off there. Chao Yang, do you want to unmute and ask your question directly? I can also read it. So it is to Mary. Do you need to adjust the constraint matrix for the L1B stack approach? If so, how do you design that?
I will do my best with this question. I think Bryant would give a much better answer. Yes, the constraint matrix is adjusted. I know Bryant uses a diagonal regularization matrix. It differs slightly from the monthly MASCONs, because I know the monthly MASCONs use a regional based block diagonal matrix, and that's necessary to reduce leakage. But whenever you use many years instead of just one single month, we have enough spatial coverage that we don't have to use the block regularization. So instead he's using a full diagonal regularization matrix. That's about all I can give. I don't know the rest of the details for how
we can follow up with Bryant. And JT, you have your hand up. Go ahead.
I was going to offer that if it's useful, there's a couple themes across the hydrology talks, like downscaling and comparison and use of models. And that it might be worth hearing some of the speakers kind of discuss their opinions on these topics. So like, for instance, like to start with downscaling, for instance, and I really love Susanna's work with GNSS and NCAR. And I noticed in your equations that there is that joint inversion, and it has that weighted matrix. And I think a question for me that always exists with downscaling is how much information actually comes from the data set you're using to downscaling, and how much information actually comes from the GRACE or GRACE follow-on observations. And I would think that this would be something you could quantify. And I think in those types of studies, for people who are doing downscaling, it would be really useful to see what fraction of the actual information in the final result comes from the GRACE and GRACE follow-on data. How is that actually affecting your solution? What does it look like with or without the GRACE data? Especially in the case of GNSS, where I've seen some really great work from Donald, Argus, and others, where there is pretty high resolution water storage information in GNSS, especially in places with dense networks like California. So I'll just leave it open maybe for...
Susanna, do you want to respond to that?
Sure, yes. That's a big question, very interesting also. I could probably say a lot of things. I have to pick though. So in our previous studies, we have done tests like that. So we did joint inversion with GRACE and GPS, and then compare that also to a to a single inversion with GPS only. And you're right. Also, in general, in Central Valley, what we know is that if you look just at the seasonal component, you can resolve that with GPS alone really well. But then when you look at the trend, you get into problems because there is some tectonic effects. There's some other things you don't have. If you do only an elastic loading inversion, you don't have data over the aquifer, which is a huge portion. So I'm not sure exactly. I would have to think about how to quantify how much comes from each data set. Just looking simply at the weights doesn't tell you always, because you have also different number of observations, but I can think about this. But yeah, it's a very interesting question.
Yeah, and it's so like to your point, there's places like in the valley where there's not many GPS stations, but there's a lot of INSAR information. So that I just think that's an interesting topic to open. But right.
Sorry, I forgot to add that in the long-term trend, I forgot to add this thought, and that's exactly what we can embrace, the long-term trend.
Yeah.
This is Donald. I want to answer that question too, because we do the GPS grace inversion, and we actually calculate something called an importance factor that tells you the relative contribution of the GPS data, the grace data, and the regularization data, because so the total importance adds up to the number of pixels. And there's a lot of pixels. They're all quarter-degree pixels. And a lot of the importance actually comes from the regularization, because you need that to get it. But then you have also a total importance for the GPS, a total importance for the grace. And you could actually weight your data between GPS and grace by using these importances. So that's what we've done in the Argus 2022 paper. Thanks.
Thank you, Donald. I see a hand up from Cosro's group there. Cosro, go ahead.
Can you hear me?
Yes.
So I just wanted to say that, first of all, that's a great question, JT. But I think the answer also depends how you do the combination, right? For example, we have this spectral-based approach using wavelets that we have developed with Susanna and Manu Shirzai. And the way that we do that in that case is that when we are doing the combination, because it's done in the spectral domain, right? So then we make sure that below 300 kilometers, everything comes from GPS. So you can do that if you are doing the combination in spectral domain, right? That's very challenging when you do it using like the spatial domain approaches. And then above 300 kilometers, then you can get most of the information from GRACE or combine it with GPS. For example, that's how we do it for the whole California. So I'm just saying that that gives you a lot of flexibility if you use a spectral approach. Does that make sense?
Yeah, of course. So in the spectral approach, you can talk about the higher order, harmonics or whatever coming from higher order coefficients coming from the other
Isabella,
data.
I see your hand up. Go ahead.
Order coming from.
I just wanted to, I'm just wondering, so there is like, what is the GPS is measuring and what the other signal is measuring, and how do we characterize, like you say, we look at more than 200, but GPS can be so sensitive to what is underneath the GPS if you look at the transfer function. So I think that's also a challenge, how to connect and extract the right information, and that's a function of how the aquifer is spreading, and maybe in air like California we know very well what is the positioning, but if we do some of those things somewhere else, we don't know how the signal is cross correlated and what we're really measuring. And so I guess there is a challenge on how do we include that, and how we include an uncertainty associated to that.
Yeah, that's a good point. I have a somewhat related question in this vein. So there are a couple talks, really exciting talks on, really looking upstream in the data, in the level 1 ranging data to infer information about surface mass change. And they're kind of on opposites end of the temporal scale. Mary presented the stacking approach, which looks at longer time scales. And then there is the sort of almost instantaneous interpretation. Cosro has talked about that, where the LGD approach, where you really look at the range rate or range acceleration and underneath the satellite. So, but you sit at far apart in the temporal sense. Are there ways, maybe Cosro and Mary, you can talk about how these approaches are related or like philosophically very different, or are there ways to bring them together in temporal space to get more of that high resolution information into the spatial domain? maybe that's how we do mass cons. That's where you end up in applying constraints or something like that. Maybe you have some thoughts on that topic, Kazuo or Mary. Sorry to put you on the spot. Others are invited
Oh
too.
no, it's great. But Mary can go first, maybe. Yeah. So you put it very clearly that we are basically looking at the both ends of the spectrum, right? So for example, I showed some information about like high frequency atmospheric, or I could show that for the flood. So that's just instantaneous measurement. So if there's a mass change here, satellite is flying above it, it sees it, right? But Mary was showing the opposite end of the spectrum, which is this long term, right? And the way that I see that it's just these two approaches which just benefit from directly looking at just a long orbit, like intersatellite data, or a way just to push the limit of grace, right? To make it, let me put it this way, broaden the applications that we can address with grace, right? So we know that we can use the monthly data to study the seasonal and interannual variability, right? But if you want to look at the trends, or like, I don't know, mean seasonal average, or these instantaneous changes, it's very useful just to look at that. So that's what I would say. But Mary, I'm sure can add more to this.
No, I would agree. I think that's put pretty well. I also think that it really depends on your application, like your desired case study. And I know that with the trend fields that we're looking at are often really satisfying to look at. You see a lot of things spatially. It's really interesting to be able to capture, we can see Lake Victoria light up, and we can see the central Amazon light up and stuff like that. But there is some information lost, and we can't look at the strength of that change or when it happens. This isn't like a monthly time series where we get a regression R squared and we can see how strong that trend is. We can say how much water has changed over the course of 2 decades, but we don't know when that happened. And so I think to me, it's more of a trade-off than it is an added information, if that makes sense.
Yeah, it does. Are there other comments or questions?
Yeah.
Felix, could I ask a question? I can't raise my hand. I've been actually silenced on this thing over here. I do not have one of these little hand buttons on my display. And so
you can always ask questions.
If you don't mind if I could ask a question. This is very intriguing discussion this morning, and it goes into the one of the big issues we wrestle with grace falling, and we'll be in continuity going downstream. The question in terms of this, it's very intriguing, at least when we were looking at these issues with Matt and the model that Goddard had over here about a lot of these questions about spatial temporal resolution is essentially handled if you get the model right going into it. There's also another factor that to me was always intriguing, and we are talking about validating the grace measurements and to some extent validating the models, but the model has the ability of doing the disaggregation of baking up the columnar measurement that grace makes into these versions over here. Are we looking at that, trying to validate those components anyway and trying to raise the question of what the validity of the model output from those when you break those up? That to me seems to be a really important point in trying to look at these hydrological measurements over there. And if we could improve the models or use the information we're getting from GRACE and the other space data to get the models right over here, we take a big step over into a lot of these questions we're looking at. You really are challenged on the GRACE measurements with this two single pair. If you can put other pairs up there, then a lot of this spatial temporal resolution, becomes apparent. But with a single pair, we're really kind of on the boundary of where we can go with those now. But the model does have potential for going into some of those areas. And I don't know whether that's an issue that's going on and I'm just behind on it, but it seems to me that something we ought to think about. Sorry, I didn't mean to get so long there.
No, I appreciate your perspective. I want to know we're almost up on time. I'm perfectly fine to hang on for a couple more minutes. I don't want to choke off the conversation, but I do want to also be respectful of your time. So if you want to jump off, feel free to do so. We can continue for maybe 5 more minutes if there's interest, if there are questions. Otherwise, we can also push into tomorrow. There's a little bit of time there. Does anyone want to comment or respond further on this topic?
Yeah,
think
just
Donald,
just
sorry,
to,
someone.
sorry, it's JT. Just to build on what Byron's saying, I mean, we saw some presentations with model comparisons or the use of models to disaggregate the gray signal, and we just have to remember that land surface models, and I saw Bridget Scanlan's face on here earlier. Land surface models, they're forced with precipitation observations and radiative forcing usually. And beyond that, there's almost nothing in those models that is real, that they tend to be really bad. They don't have correct soil depth. They don't do a great job with snow. They have different ET parameterizations. And when they try to do water balance, or even runoff generation, drainage, all these things, if you look at 10 different models, you seriously get 10 different answers. And GRACE is a weird observation as well, right? But in comparing GRACE and models, or using GRACE follow-on, and models to disaggregate, I think we just have to be careful and creative in how we're comparing them. And one thing that's been kind of done over the 20 years or so of publications now that we have with GRACE follow-on is using ensembles of models. That if you can use more than one model, you might get a couple different answers, and maybe that spread can give you some sense of a beginning of the uncertainty that you're looking at with these models. But definitely interesting area for continued work.
Is the physics just not known, JT, or is it just that we're not putting the effort into improving the physics of the model?
Yeah, that's it, Byron. There's really very few observations of the subsurface. So actual probing of the subsurface to understand the geologic matrix that sits there. I mean, in areas where they do oil exploration, we know it's happening. But for the rest of the world, below the top meter or so, we don't really know what the geology is. And so it's hard to understand how long the water is going to sit in the subsurface. In the Central Valley in California, there's water tables that are 100, 200 meters deep in some places. They're really, really deep. But there's a lot of water down there. We just don't know. Hard to see.
I'll make one question and then I'll drop off of this thing over here. Is it not likely that the big ticket item in there is the soil moisture, the near surface though? If you could get the physics right on that, then what's left over, you may not be able to model it correctly, but what's left over is this impenetrable groundwater aquifer, which is very important to know what's going into it. But being able to break up that first part, get the errors in that part out, seems to me to be one place where physical modeling might be possible there.
Yeah, it's good. That just depends on evapotranspiration parameterizations and runoff generation and things like this. And yeah, but that's a open field of research.
Isabella, you've been patient with your hand up, so go ahead.
Yeah, I just make a short comment. I do think there is a potential of target of opportunity. We have a model and we want to evaluate the model globally. And to me, it's like, can we find, some cases in which there are some processes that are dominant and then use observation in a, diagnostic way? Can we see, and so because we have so many components. And so to me, there is a lot. And observation could be satellite, depending, maybe we don't understand the process at the scale of, 100 kilometers or 10 meters or whatever is needed, but we understand what is the regional uncertainty. And I do think that has potential, and it takes putting together people that really understand about the local processes and the cross correlation of the signal, the model, understanding how the parameterization is done and what assumptions have been made, and people that really understand the observation and the uncertainty and just figure out some target and start from there.
Susanna, go ahead.
Took me a moment to figure out how that racing works. Okay, I just wanted to add to this really interesting points also that were just made. I think it's also a scale issue. So we have this, especially for the subsurface, we have this really heterogeneous reality down there in the subsurface. And and we have really few observation of that, especially when you think about the groundwater and the aquifers and the soil and how that all splits up, and really going from the local observations, few observations that we have, and the heterogeneous reality to this really large scale observation we have from GRACE. So that's really a big challenge, I believe.
Yeah, excellent discussion. I really appreciate it. I said we could add 5 minutes on. We've reached those 5 minutes. I feel like we there's a lot more here to follow up on, and maybe we can actually take this as an incentive to set up a group out of this meeting that discusses these themes down the road. We don't just do that on an annual timescale where we scratch the surface and then we go back to our little offices and cubicles. But we'll take that. Maybe JT and I, you can stick our heads together and organize something and reach out to everyone that's on this call, and you can then participate, and we can take that to the next level with some organized themes and problems that we want to tackle. I think I sense there's quite a bit there, and this intersection of higher temporal spatial resolution. Of course, that's always something that users of our data want. There are a lot of caveats that come with that. Those are already touched on. But if we communicate that right, I think we have a very good chance of having our data sort of get disseminated and used correctly in many more ways, and that will also further the cause for future missions and getting our work funded, which is an increasingly important topic, as you know. So on that note, I want to thank everyone for participating today. Great turnout again. We'll have one more day tomorrow, a little bit shorter. Same time though, same kickoff time. And any overflow discussions we can also have then. So thank you. Have a great rest of your day for those in the US, and have a good evening for those in Europe. And we'll see you again tomorrow.
I am going to leave this meeting running for a few minutes. If anybody who's presenting tomorrow wants to test, Don, I know you do, but just stay on the line and we'll get you all sorted out.
Thank you, Colin. Great call. Appreciate that. Okay. See you all tomorrow. Bye.